Our next topic is torque on the current carrying rectangular loop placed in uniform magnetic field. This is also very important topic. Torque on current carrying rectangular loop placed in magnetic field. This is rectangular loop. A, B, C and D, and the current flows through this rectangular loop. Current is flowing through this rectangular loop, and this rectangular loop is placed in the magnetic field B. Here all lines are parallel, that is, this rectangular loop is placed in uniform magnetic field. This is the normal vector of this rectangular loop, n vector, and remember this normal vector and these are the magnetic lines. These forms an angle theta between them. Theta is the angle, and remember theta is the angle between the normal vector, that is the vector perpendicular to the plane, and the magnetic lines. This is the magnetic field line and this is the normal vector. Remember this thing. Second thing, see the direction of the current here and here. You know well, these two arms are perpendicularly placed within the uniform magnetic field, length L and the magnetic field. So when the current carrying conductor is placed within the uniform magnetic field, it experiences force, which you studied earlier. The force experienced by the current carrying conductor will be F will be I L cross B. Here length L and the B, here both the two are making an angle 90 degree, therefore you can write it as BIL only. So this is the force experienced by the wire AB. Now of this rectangular loop, for the second wire, see DC part, the current flows here will be B to A and here D to C. So the force experienced by the DC wire will be equal, because both the current is constant flowing through this rectangular loop, but in opposite direction. If F1 is here, if it is F1, then F2 will also equal in magnitude, but see the direction of the current. Is the current flows in the same direction? No. Therefore, if the current is in opposite direction, force experienced by this wire will also opposite in direction. See, this is the direction of F1, this is the direction of F2, opposite in direction, and the force at the F1, the point where F1 and F2 are acting, is not a constant force or not a common force, you can say. So F2 is also BIL, but this will be opposite in direction. Therefore, you will use negative sign. Therefore, net force will be 0. F1 and F2 equal in magnitude but opposite in direction, and the point where F1 and F2 are acting, it is not a common point. Therefore, like this, if at the point A, F1 is acting in this direction, at the point D, F2 is acting in the downward direction, because current is flowing in opposite direction. This is the B part, like this, So the point where F1 and F2 are acting is not a common point. Hence, torque will be experienced by this coil. If torque will be experienced by this coil, then the complete coil will rotate within the magnetic field. So, the torque experienced will be force, either force into perpendicular distance. Either force, either this or this, because both the forces are equal, you can write it as BIL, and perpendicular distance C. Theta is the angle formed with the normal of this plane and the magnetic line. So this angle is theta. Perpendicular distance, this is B, this is B, this is B, this complete is B. Therefore, this perpendicular distance will be B sin theta. B sin theta. It is length into breadth. It is area of this rectangular coil. You can write it as BIA sin theta. If you have n number of turns, because at present it has only one turn, single turn, if there are n number of turns, then it can be written as NBIA sin theta. So this is the torque experienced by the coil, current carrying coil placed in the uniform magnetic field. Let's consider the different conditions. First of all, if theta is 90 degree, what is the meaning? Theta is 90 degree. Theta is the angle between normal of this plane and the magnetic line. If magnetic lines are moving like this, for example, magnetic lines are like this and the plane is like this. This is the normal of the plane. Magnetic lines are moving like this. Normal of the plane is this. So, normal of this plane and the magnetic lines, see, these are the magnetic lines. This is the normal of the plane. That is, plane is along the direction of magnetic field. What meaning? Remember, see the diagram. These are magnetic lines. This is the normal to the plane. Normal to the plane, normal to this plane, and this normal making an angle 90 degree. That is, plane and magnetic field are parallel to each other. In this condition, if theta is 90 degree, that is, plane is along magnetic field, right? If theta is 90 degree, then this value will be tau is equals to NBIA only, and it is the maximum torque. NBIA. What is the minimum torque? Or you can say, if theta is equals to 0, what does it mean? Theta 0 means what? As we studied earlier, this is a plane, this is the normal of this plane, and these are the magnetic lines. Now theta is 0. At present, theta is 90 degree. If our coil, these are the magnetic lines, remember, if our coil moves like this, now normal to the plane and the magnetic lines both are in the same direction, and here at present theta is 0. But what about this plane? Plane makes an angle 90 degree with the magnetic field lines. If theta is 0, that is normal to the plane, this is the plane, This is the normal, this is the magnetic field. Magnetic field and the normal making an angle 0. Theta is 0, sin 0 is 0, so torque will be also 0. So under what condition torque will be maximum? Under what condition torque will be maximum? If this is the plane, this is the normal, and normal makes 90 degree like this. That is, plane makes 0 degree angle, or you can say normal makes 90 degree with the magnetic field lines. This is only possible if we have radial magnetic field. So students, we prefer radial magnetic field. Radial magnetic field means normal will always have 90 degree, or you can say plane makes an angle 0 degree. Plane makes 0 degree angle, normal makes 90 degree angle. So this is only possible if you will apply radial magnetic field. Friends, this is the shape of radial magnetic field. This is our rectangular coil. If you will see from the top, these are the magnetic field lines, that is, poles are slightly curved. See the shape of the poles, they have curved poles. So magnetic lines are moving like this. If the coil is placed like this, so the coil and the magnetic field lines, they are parallel to each other. This is the normal. Normal makes 90 degree angle with this magnetic field line. Here the plane of the coil is along the direction of magnetic field. If it rotates like this, if it comes over here, again this line is parallel to this coil. If it rotates like this, this plane and the magnetic line is along the same, both are theta is equals to 0, phi is equals to 0. So under every condition, the normal to the plane and the magnetic field lines are perpendicular. So there will be maximum torque under every condition. Hence we prefer radial magnetic field. So this condition is only applicable for radial magnetic field. This is only applicable for radial magnetic field. That is, theta will always 90 degree, perpendicular, normal to the plane and the magnetic field lines, or you can say plane makes 0 degree angle. So torque will always NBIA. Here we will study about moving coil galvanometer. Basically, it is a device used to detect small current. It can detect small current. Principle. On what principle? When a current carrying loop is placed in uniform magnetic field, which you studied in last topic, when a loop in which current I flows, if it is placed in the uniform magnetic field, it experiences torque and the loop rotates. This is the principle of that. Now let us see the construction. See the diagram. These are the two magnetic poles, north and south. Now you can easily judge what type of magnetic field will be developed by this type of magnetic poles. It is radial magnetic field, as you studied earlier. So radial magnetic field in which theta is always 90 degree, or the coil always along the direction of the magnetic field. This is a soft iron core on which large number of turns of insulated wire is wounded on it, and on each turn I current flows. This is a phosphor bronze wire by which this core is suspended within the magnetic field. Now, next very important part, it is a spring which is located just below, and this part is fixed. This part of the spring is fixed. Now see the working. Here already B is the intensity of the magnetic field in which the current loop or the rectangular coil is placed. L is the length of the coil. A is the area of cross section, and N are the total number of turns on this soft iron core. Now let us see the working. If this loop in which current I is flowing, if it is placed in the radial magnetic field, then what happens? It experiences torque, and the torque experienced within the radial magnetic field will be NBIA. This is the maximum torque experienced by the coil within radial magnetic field. Number 1. Now, if this coil rotates at a particular angle, whatever be the angle, and this needle shows the deflection, if this coil rotates, if you stop the current which is flowing within this rectangular loop, then what happens? Due to the spring, this or the rectangular loop will come to its original position. Due to which part? Due to the spring which is located just below the rectangular loop. So the restoring torque by the spring which is located just below, it brings the rectangular loop into its original position. Therefore, it will be C theta, where C is the couple per unit twist and theta is the angle deflected. Angle deflected during the rotation, theta, or you can say you can choose any angle, because theta previously we have taken, so you can take it as C alpha, where alpha is the angle rotated by the needle or by the coil. This is the restoring torque. This is deflecting torque. Therefore, NBIA is equals to C alpha. This is the condition. The deflecting torque will be equal to the restoring torque. Hence, NBIA is equals to C alpha, which you already studied. I is equals to C upon NBA into alpha. Now C is the couple per unit twist of the spring, which is constant, because a constant spring is fixed, you will not change for a particular galvanometer. N are the number of turns on the soft iron core. B is the applied magnetic field, which is also constant. A, area of the core of the soft iron. Therefore, this complete value will remain constant for a particular galvanometer. Therefore, I is equals to G alpha or I is proportional to alpha, where G is called galvanometer constant. G is galvanometer constant, which is equal to C upon NBA. This is the constant of the galvanometer, and all the values are fixed during the construction of a particular galvanometer. So this is called G, and this shows that this particular expression shows that greater be the current, greater be the angle deflected. That is, angle of deflection is directly proportional to the current. More be the current flows through the galvanometer, the angle deflected by the galvanometer will also more. Now we will study about current sensitivity of a galvanometer. This is also very important. It is deflection produced per unit current. What is the meaning of current sensitivity? Deflection per unit current. For example, you have two galvanometers. If you will flow a same current to both of the two galvanometers, and the first galvanometer producing 10-degree deflection, second galvanometer is producing 30-degree deflection, which galvanometer is more sensitive or accurate? Naturally, the galvanometer where the deflection is 30-degree, because constant same current is flowing through both of the galvanometers, and the second galvanometer more deflection is there. Therefore, second galvanometer is more sensitive. If more deflection for a particular current, angle deflected per unit current, if it is more, then the sensitivity of the galvanometer is also more. Deflection produced per unit current. Now, this is the condition which you studied here. Deflection produced per unit current, alpha upon I. It can be written as NBA upon C. This is the deflection produced per unit current of galvanometer, and it is this. N means total number of turns. Now see, it is very important. This is also called current sensitivity of galvanometer. Current sensitivity of galvanometer may increased if you will increase number of turns on this soft iron core, if you will increase magnetic field intensity which is applied by the two poles, north and south poles, area, on increasing area of the core, sensitivity will increase, and on decreasing the couple per unit twist. That is, if you are using a soft spring, then the current sensitivity of the galvanometer increases. Remember the conditions on which the current sensitivity depends upon the four things. What are the four things? N, B, A, these are directly proportional, and C is inversely proportional. C is inversely proportional, NBA is directly proportional. So, on these factors, the current sensitivity depends. On these factors, remember these factors. NBA directly proportional, C inversely proportional. Now, second thing, voltage sensitivity. what is the meaning of voltage sensitivity? It is alpha upon V, the deflection produced per unit applied potential. Deflection produced per unit applied potential. Now see this expression. Again, NBA upon C is equals to alpha upon I. Here, if you will multiply it by R, here you are multiplying by R. This is what? According to Ohm's law, it is V. Therefore, it can be written as alpha upon V. This is called voltage sensitivity. See, so what is voltage sensitivity? Voltage sensitivity will be how much? NBA upon R into C. This is voltage sensitivity. So, how can you increase voltage sensitivity? Remember, if you will increase P, more applied magnetic field, voltage sensitivity will increase. Increasing area, voltage sensitivity will increase. Decreasing couple per unit twist of the spring, voltage sensitivity will increase. Now remember these two, this N and this R. If you will increase N, means if you will increase number of turns of the core of the coil which is bounded on the soft iron core, if you will increase N, on increasing N, resistance of the wire will also increase. Remember this condition. When the length of the wire increases, you studied in the current electricity chapter, when length of the wire increases, resistance also increases. Therefore, if N increases, resistance will also increase. This will increase, this is also increase. So, there will be no effect, as a result of which there will be no effect on increasing N. If you will increase N, resistance will also increase, both will cancel out, so there will be no effect on increasing number of turns which are wounded on the soft iron core. But see in the current sensitivity, if you will increase N, current sensitivity will increase. If you will increase N over here, R will also increase, no effect on voltage sensitivity. Therefore, this question generally comes that on increasing number of turns, the current sensitivity will increase, but the voltage sensitivity on increasing number of turns, resistance will also increase, no effect will be there, that is voltage sensitivity will independent on increasing number of turns. After the galvanometer, now come to the ammeter. We will study ammeter and later on how a galvanometer can be converted into ammeter, because basically galvanometer is used to detect the presence of current in the circuit, whether the current is present or not. Now ammeter is used first of all to measure the electric current in the circuit, how much amount of current flows in the circuit. This is that particular instrument, and that instrument is called ammeter. Remember students, ammeter has a very low resistance. Overall, ammeter has a very low resistance, because if the resistance is high and the current is flowing through that, then what happens? It consumes electric current and it will not give you the accurate value of the current. Therefore, it has particularly very small value of resistance, or ideal ammeter has almost zero resistance. Remember that. Now, if you want to convert a galvanometer to ammeter, as I stated here that galvanometer has certain resistance, because in the previous article we studied that coil are wounded on the soft iron core and these coils have certain resistance. Therefore, if the resistance is there, definitely that particular galvanometer cannot measure accurate amount of the current. Therefore, we have to decrease the value of the resistance of galvanometer, and resistance of galvanometer can only be decreased if you will connect a resistance across its parallel. Then suppose this is a galvanometer and you want to convert this galvanometer into ammeter. So what you have to do? You have to use or you have to connect a resistance, a low resistance, let it is shunt. This resistance has S ohm. Let I current flows through it and you want to measure this particular current. Then if the resistance of galvanometer is G, let the current flows here is Ig. Ig is called full scale deflection current. That is that particular current which gives you the complete deflection of the needle. This amount of current is Ig, full scale deflection current of galvanometer. If I is coming out from here, Ig goes from here, what is the remaining value of the current? Remaining value of the current will be I minus Ig. This is the remaining value of the current, and this I minus Ig flows through the shunt. Shunt means a parallel resistance across the galvanometer. This is I minus Ig. Ig comes from here and therefore this current is also I. Now across the terminal AB, this is A and this is B, the potential difference across the galvanometer and the potential difference across the shunt is same as per the circuit. See these two terminals. Therefore, the potential difference across the galvanometer is G into Ig. Current into resistance. Current is Ig, resistance is G, and this will be equal to the potential difference across the shunt. See, and the potential difference will be S into I minus Ig. Therefore, S can be written as Gig upon I minus Ig. So this is the value of the shunt. Now this formula is very important. How can you define this formula? This is the shunt. This is the resistance required to be connected across parallel when you are measuring the current I. Then that particular galvanometer will be converted into ammeter, where the galvanometer resistance is G and Ig is the full scale deflection current of the galvanometer. So all these, this G, this Ig will remain constant for a particular galvanometer. In order to measure the I current, put the value of I, you get the value of shunt. So when you connect a resistance across parallel, you can measure the I amount of current, and that galvanometer will be converted into ammeter. Our next topic is voltmeter, and later on how can you convert a galvanometer into voltmeter. First of all, voltmeter. Voltmeter is a device which can measure the potential difference between two points. And if it measures the potential difference, this shows that the resistance of the voltmeter is very high. When the resistance is very high, then only it can measure the accurate value of the potential difference. For example, if current is flowing from here, you are connecting a voltmeter over here, and the resistance is, if it is very high, then it gives the potential over here and no current over here. Then only you can measure the accurate value of the potential difference. If the current is flowing here and it is also leaving out, it means this voltmeter will not measure the exact value of the potential difference. So, how can you convert a galvanometer into voltmeter? Galvanometer has a certain resistance. If you will increase the value of resistance of galvanometer, it will be converted into the voltmeter. And that is only possible if you will connect a shunt resistance along the series of the galvanometer. For example, if this is a galvanometer and you want to convert this galvanometer into voltmeter, then you have to connect a resistance, high value of resistance S with the galvanometer. Let Ig is the current passes through the galvanometer, and that particular current is also passing through the shunt. So, what is the net resistance? G is the resistance of galvanometer, S is the resistance of the shunt. Both of the two are in the series. So, net resistance is how much? G plus S. Net potential difference will be how much? Potential difference V can be written as net resistance into current, that is G plus S into Ig, net resistance and current, or V upon Ig, G plus S and S. This is the value of the shunt resistance. So, this shunt must be connected along the series of the galvanometer, because G is a constant, Ig is a full scale deflection current which you can measure. Only if you want to measure the V potential difference, then you have to connect S value of resistance with the series of the galvanometer. Then this galvanometer can be converted into a voltmeter.